Or you can get Paul slide.
You know? Perfect. Awesome. Well, thank you for the introduction. Today I wanted to discuss some work I've been doing during my PhD on Sputnik Basin, specifically trying to constrain its subsurface structure, its present-day compensation state, and then how this is intimately tied into Pluto's evolution and its interior. So we'll review Sputnik Basin a bit. I know we talked a lot about it, but we're going to look at a bit of structural characterization here too. So Sputnik Basin is a 2,000 by 1,000 kilometer elongated impact basin in the equatorial region, shown here in the stereotypography over on your right. It's got a decently well-defined rim towards the north, tapers towards the south, kind of this messy, undefined tail at the end. It has this north to south trending chain of water ice mountain blocks that we see in the western half of the basin. There have been a series of interpretations of that. We're in favor of peak ring, and we'll discuss that a little bit later. The basin's also partially infilled with N2-rich ice fall deposits, Sputnik Planitia. We've also talked a lot about that. Its depth is unknown. We've got some range of estimates between 3 and 11 kilometers, which is pretty large, but it's pretty unconstrained. We can also see that it extends almost towards the north end. We saw some discussion about some of those dark plains kind of earlier, and it sort of stops part of the way to the eastern rim and kind of doesn't go all the way into the tail. This deposit has the polygonal pattern on its surface. It's interpreted to be convection cells. And another interesting piece is that the size of the convection cells are largest mostly in the center and get smaller as you go towards the edges, indicating that it's potentially decreasing with size from center to edge. Sputnik Basin is currently aligned with Pluto's tidal axis, and we again talked about this earlier, but the basin's alignment with that axis has led to the hypothesis of reorientation of the basin through true polar wander. The consequences of reorientation, the basin needs to have been initially isostatically compensated by a high-density ocean layer, and then loaded with that N2 load to essentially induce a positive gravity anomaly and true polar wander. So Sputnik Basin needs to have been a positive gravity anomaly in the past. The thing is, we have no spatially resolved gravitational data and no direct constraint on the present-day state of the basin or the existence of the present-day subsurface ocean or how that connects to the previous reorientation. So what I aim to do here is to answer a few questions. What constraints can we put on the compensation state and present-day mass anomaly of the basin and the structure beneath it? And what are the implications for the structural, thermal, and deformational evolution of the basin? What implications those have for evolutionary pathways for Pluto's history? That's a mouthful, and I'd love to be able to answer it all, but my goal here is to just contribute a drop in the bucket. We're going to take a bit of a better look at its structural characterization, some aspects here, because as we've seen on other objects, what we see in the surface sometimes gives us clues into what the subsurface may look like. We're going to return to that north to south trending chain of water ice mountain blocks, and a couple of interpretations have been proposed. The blocks could have been mobilized of the fractured water ice crust, and then essentially in place in nitrogen ice. They're either floating and then becoming grouted, or there's basal sliding occurring at the bottom after it's been fragmented, or they could be the remnant of an exposed peak ring. In fact, the McKinnon's 2017 abstract points out that there is a notable root 2 characteristic spacing between the chain of water ice mountain blocks and the rim that we also note in lunar and basin rings on the moon. Now, what I've done on the right here is essentially outlined what Sputnik Basin's rings would look like, the outer ring being the rim, and the inner ring tracing the inside edge of that water ice mountain blocks. And what do I mean by peak ring? I've done a nice morphological comparison here between a peak ring, Hertzsprung on the moon, a molten ring basin Oriental, and what we're considering a giant impact basin that's Hellas on Mars. A peak ring basin, again, has your inner ring and a ring defined by the rim. You end up with a central uplift that is constrained within the inner ring. Molten ring basin is similar. You've got this additional middle ring, and your uplift is constrained in the middle. Giant impact basins are typically larger in dimension. They're more elongated. They have one ring defined by the rim, and you've got uplift throughout the entire extent of the basin. Again, we have no gravity data to put constraints on this. That's what we do a lot with the moon. So we have to sort of use comparative analyses between lunar and Martian basins and Sputnik Basin to take a look at what we can constrain. I'm going to run through this a little bit quickly. I'm happy to talk about this later, but in order to do a topographic analysis, we have to reconstruct what Sputnik Basin looks like pre-fill, and there's a wide range of depths it could be based on aspect ratios of convection cells and how much flex you get, but we can then use that reconstructed Sputnik Basin to compare to topography or topographic profiles of other basins on the Moon and Mars, finding that it's topographically consistent with a peak or multi-ring basin. We also run statistical analyses, ring ratios, center thinning, ring depths, etc., and find that Sputnik Basins typically falls within a sigma of a lot of these different statistical analyses, finding that's also statistically consistent with peak ring basins. So here what I've done is essentially put up what a giant impact basin subsurface would look like radially, a radial topographic radial profile here, peak ring on the bottom, and our estimates of what Sputnik may look like. If Sputnik Basin is a peak ring basin, as it seems to be topographically, morphologically, and statistically consistent with, then any uplift of that ocean would be concentrated within the inner ring. We also end up with a decrease, so you decrease that uplift you would have assumed before by almost 35%, which actually has some impacts for the impactor dimensions too, decreasing that size. Now that we have another theory of what the subsurface may look like, we're going to try to invent gravity. Not really. But essentially what we're going to do is make this assumption that the N2 deposit, such low viscosity, follows an equipotential surface. And so the topography of the Sputnik Basin essentially should conform to Pluto's geoid. This allows us to put constraints on the gravity field over the basin. Now we see in topography on the right and an east to west average profile on the bottom right here. And there is a characteristic concave up shape in the center of the basin. We find this for a slew of profiles, whether it's individual or average. If Sputnik Basin kind of topography conforms to a geoid, and a concave up geoid is typically a mass deficit or a negative gravity anomaly. Something that's a positive gravity anomaly or a mass excess would have a concave up shape. So what we do is use a thin shell deformation model to calculate the geoid and gravity for a range of what we call compensation states, shell thicknesses, interlayer thicknesses. And essentially what we're doing is calculating the gravity from deflections of interfaces beneath Sputnik Basin. And then because we made this assumption that the N2 deposit should conform to the geoid, we can compare directly the range of different geoid models to the topography itself. And we run through a series of other different types of inputs. So when I say uncompensated basin, we measure it by degree of compensation, which is close to 0 or sometimes less than 0.5. Isostatically compensated is a degree of compensation of 1. Overcompensated, we're looking at 1.5. We have a large range of shell thicknesses and N2 layer thicknesses too, and attempt to put some constraints on those. So we do a simple qualitative analysis. I've got an example here up on the top left. East to west profile is again in white. Your different geoid models are in color, and your peak ring structures are in dashed lines, your giant impact basins in solid. And essentially what we find qualitatively, at least, is that an undercompensated basin, something has a degree of compensation less than 0.5, is essentially required to fit that concave up shape. So Sputnik Basin may best be represented by a present-day mass deficit. We run a series of RMS misfit analyses, finding that corroborates our results. And so our takeaway point is that Sputnik Basin is most likely largely uncompensated in a mass deficit today. So we have a positive gravity anomaly that most likely induced reorientation, and then we end up with a present-day mass deficit. How do we reconcile the two? So let's say we start with initially isostatically compensated basin, gravity geoid-ish near 0. Mass excess is generated from the infill, that infill of the N2 deposit. We reorient Pluto, and then in Sputnik Basin's present-day location, the uplifted ocean beneath the basin refreezes with time. That could transition our basin from a past mass excess to a present-day mass deficit. To try to do this quantitatively, we've essentially developed a thermal model based on many of the previous work that's been done before. We utilize a fully explicit finite difference thermal diffusion model and spherical geometry. Our heat flux is really only generated from just radioactive decay. We don't, at this point, include any of the other sources of energy we've talked about before. We consider two initial thermal states, the cold start, fully solid hydrosphere, or the hot start initial condition with an existing ocean. We end up doing two different types of thermal distributions within the hot start in the sense that we consider initially isothermal temperature distribution at approximately the average accretion temperature, as well as a initial temperature distribution that is in equilibrium, which is sort of what's shown here on the bottom right, with different evolutions of your radiogenic heat flux with time out of the core. And then some of the dashed lines are, I sort of scale it to the base of the ice shell. We also include different pieces that would help to inhibit refreezing. So we have insulation from the N2 deposit inside the basin. We've got insulation from a potential methane clathrate layer at the base of the ice shell. And we have the existence of ammonia in the subsurface ocean that tends to decrease the temperature. So here are the results essentially for the cold start model. On the top left here, we have the simulation running for 0 to 4.5 billion years, present day, shell thickness shown in the y-axis. And there are a couple different model results shown here. Your solid lines are outside the basin. Your dashed lines are inside the basin. If we look at the thermal evolution of Pluto's ice shell in two different scenarios and then compare them, we can track degree of compensation, essentially, of the basin through time. For a cold start model, we end up with a essentially decreasing ice shell. We're forming an ocean. The impact basin happens. We've assumed 500 million years into Pluto's history, but our results don't really change between 100 and 800 million years. And then by about 1.5 billion years after the impact, our ice shells have effectively reached equilibrium, and we enter this later phase of cooling that's mostly governed by decreasing radiogenic heat flux. If we include a methane clathrate layer, we do end up with a larger ocean at present day, but the difference between our present day ice shell beneath the basin and outside of it is pretty similar to what we have. We didn't include a methane clathrate layer, and that's about approximately a 10% difference. Similar idea if we do it for the hot start model. We end up with a refreezing over time, but our final present day shell thicknesses between outside the basin and beneath the basin tend to be very similar. Now, if we take all that and we sort of track this change in degree of compensation state with time, we find that, and we start off with initially isostatically compensated basin, degree of compensation 1, and we quickly transition to an undercompensated basin within 1 billion years after the impact. We also find that if we don't include the N2 insulation, the basin essentially, ice shell beneath the basin almost refreezes to the same thickness as outside. Inclusion of the methane clathrate layer affects the degree of compensation, but it's still undercompensated. So this is a plausible transition to help the basin go from mass excess to mass deficit. I'll leave my conclusion slide up here. I got like a minute and a half, so I'm happy to take any questions.
Questions? We have time for a few.
Oliver White, SETI Institute. Regarding the peak ring hypothesis, have you wondered why maybe the sort of mountains seem to only occur in the western part of Sputnik, Planitia? There doesn't seem to be anything in the eastern part.
Yeah, that's a great question. So we have a couple of ideas as to why we only see the peak ring exposed in the western section, not in the eastern section. First of all, there are a lot of lunar basin rings or lunar basins that are degraded peak rings where only half the peak ring still exists. If Sputnik Basin formed very early, again, 4 billion years ago, maybe the N2 deposit sort of eroded part of the peak ring away. Potentially it's buried in the eastern section. And then our other idea is that it still exists. It's just that the N2 deposit has overflown it essentially on that western or eastern portion. So you're unable to actually see it in the topography.
All right, thanks.
One more quick question. Anyone with a quick question? I believe you. Quick question from me.
Yeah.
How do you estimate the initial, for your hot start versus cold start, how do you estimate the initial and final thicknesses of the interior of the basin? Because you start out with defined ice shelf thicknesses. How do you estimate the thinned ice in the basin?
Sure. So the thinned ice in the basin is essentially estimated because when you the depth of the basin can be determined from your N2 thickness. If you're assuming it's ice statically compensated, there's going to be a mathematical connection between the two based on your densities and the simple ice static ratio. And that's essentially how much we thin the shell by when we immediately impact. Cool. Thanks, guys.
All right. Thank you again.